Welcome back, everybody, after lunch. Welcome to the last session of CHES 2017, the session on efficient implementations. And it's my pleasure to introduce the first speaker, Anthony Journault, who will be presenting a joint work with François-Xavier Standaert on very high order masking, efficient implementation, and security evaluation. Please.
Thank you for the introduction. So I will start my talk with a background about masking, and more specifically about the bar-total masking scheme. And then I will try to answer the two following questions. Is it possible to implement a very high order masking scheme quite efficiently? So very high will mean in this talk with 32 shares. And then the next question is how can we evaluate the security of such an implementation at such an high order? So first, what is masking? So masking is one of the most used countermeasure against sectional attack. So basically you have your secret value A and you split it in different shares. And d-1 of these shares are computed randomly. And the last one is computed accordingly to the previous one. And we want also to look at the security of the masking countermeasure. So we have essentially two sides. One side which is to look at the abstract security, so which is given by the probing model. So in the probing model we can have more than d-1 security at best, because if we had the d probes on each of the shares, we just recover the secret. And on the other side we have a more concrete security model, which is given by the noisy leakage model, when we want to have some bounds on the number of samples we need to attack a scheme, and which is given by the noise with an exponential growth in the security order. So the bar-total masking scheme is a scheme recently introduced at Eurocrypt 2017. I will only speak about its main features, which is to handle all the shares in parallel. So instead of, like, for example, ISW, where we manipulate we do computation of the shares at different cycles in time, here we manipulate all the shares at once. So to illustrate that, I give the example of the multiplication of this scheme for d equal 3 shares. So first we need to compute the cross products between the two value A and B, between all the shares. And then we just interleave some fresh randomness between those cross products. And here we can already see that all the elements of each vector can be manipulated in parallel. So now let's take a look at how we can implement this scheme quite efficiently. So we made our implementation on a 32-bit device, and we choose this kind of representation that it's 32 of the bits of the register will contain the 31 shares, and so 31 random bits. And the last one will contain the secret bits plus the sum of the other random bits of the register in order to make everything correct. And we can quite naturally see that if we use the bitwise operator like the XOR, the AND, and so on, we have a natural parallelization over the shares when we do such operation. So in practice, we implement it on a 32-bit ARM device, and we only focus on the optimal case, on what we call the optimal case, when the number of the shares is equal to the size of the registers. And on an ARM device, this is very useful because all the rotation we need to perform the multiplication can be done for free thanks to the barrel shifter. And also note that this kind of representation can be very well suited for bit-size ciphers. So bit-size ciphers are ciphers where the S-box can be quite efficiently represented thanks to gates. So we applied this scheme to DAS. The DAS is not naturally a bit-size cipher, but we have, thanks to Boyer Peralta, quite efficient gate-level representation of its S-box. So the total number of clock cycles of DAS is around 3 million cycles. And we choose specific settings for the random value. So we choose to, it needs 10 cycles in order to generate a 32-bit random value. So what we can see here in the result is that it's not a surprise, but the linear operation is quite negligible at such an high order. So non-linear operations are still a big part of the computation, and maybe there is still optimization to do in this part. And something which is a bit more surprising is the amount of randomness we need in our computation. So specifically in our case, it can be explained because we choose to be very conservative when we looked at the probing security. So we choose to put SNI refreshing to each to one input of each multiplication, which explains the level of randomness. So yeah, I forgot the 10 cycles were chosen in order to be comparable with a work of Goudarzi and Rivin. And we also have another setting for the cost of the randomness, which corresponds to what we had in our TRNG, which is about 80 cycles to generate 32-bit random value. And here we see that the randomness takes mostly everything. Now we wanted to compare to a previous work, the work of Goudarzi and Rivin, which was published at Eurocrypt 2017. So they implemented the generic ISW masking scheme, so Ishai, Sai, and Wagner, and they applied it also to the bit slice AES. So we can see that we are a bit faster than them, but it's not really important because the two schemes are not the same. So the Barthelson masking scheme needs a bit less computation and a bit less randomness. And my conclusion will be more that these two works have the same order of magnitude in terms of clock cycles, and that there are proofs that we can implement very high orders masking, and it is not out of reach. So we have answered the first question positively. So is it possible to have something quite efficient with 32 shares? Now remains the question on how we can evaluate the security of such an implementation. So usually when you have an evaluator, the evaluator has some computational power, and he has also the more important metric international, a number of measurements. So we can just launch attacks on an implementation or do leakage detection tools. And we have essentially two cases. So if the implementation is under the power of the evaluator, the security of the implementation is under the power of the evaluator, so the evaluator can give some actual security level of this implementation. But we have the other case, or if the security is bigger than the evaluation power. And in this case, we cannot, the evaluator cannot give an actual security evaluation. It just can have security claims which are bounded by the power of the evaluator. And in our work, as we have, we manipulate 32 shares, we expect at this point to have security order 31. And even though they could have some float, so the parameter f, which reduce a bit the security, we believe that we will be way higher of which will be possible to do. So our strategy was to use what we call the multi-model approach. So in cell channel, you have generally three main models, so the probing model, the bounded moment model, and the noisy leakage model. And each of these models can bring something different in terms of security. And what we want to do is to extract this security notion of each of the models and then combine them to have something as accurate as possible. So first, we have the probing model. So it's a more abstract model we have. So from this model, we can deduce an actual algorithmic security order. So usually what we do is just to look at the algorithmic level, look all the operation, and use, for example, formal methods in order to assess the security. We have a more intermediate model, which is the bounded moment model. So it's a more physical model, and what we want to extract from this model is the physical security order. And we can do that essentially by launching leakage detection test. And we want to capture the possible behavior of share recombination. That is that if you have transition of glitches in your implementation, we want to capture it with this model. And something to note here is that these two models are completely qualitative. So from the algorithmic security order and the physical security order, we cannot make a correlation for the actual number of samples we need to attack the scheme. So we need a more concrete model, the noisy leakage model, which is a completely physical model. And it's quantitative. So from the noise we can measure for the device, and from the mutual information we can measure for the encoding. We can have some bounds on the number of samples we need. And in the end, what we want to do is to gather everything, so the algorithmic security order, the physical security order, the noise, which is given by the SNR, and the mutual information to have an actual security level of our implementation. So first, we have the providing security. So this is completely state-of-the-art, so we didn't do anything new for this one. But we have still two possible options. So the first option we choose, the first option is the one we choose is to use composable gadgets which are SNI. So it's very simple to analyze since they are composable, just have to plug them. But the implementation, as I show before, can become very expensive in terms of randomness. And another solution, which is more something of a future work, is that we can make a full code evaluation. So we just describe all the operation and make refreshing only when it's needed. But it's very hard to analyze, of course. But for this solution, we can expect to have a reduced implementation cost. So now for the bounded moment security. So as I said, we cannot just launch a leakage detection on our 32-bit or now 32 shares implementation, because we just won't be able to see anything a priori. So what have we done? We have taken an idea which is similar to what we have in symmetric cryptanalysis, that is having a security based on a reduced version. So generally, for example, for a block cipher, what you have is that you have a heuristic on a small number of rounds that you can evaluate, and the overall security of your block cipher, you will extrapolate them from this small version to the bigger version. So what we have done is to do leakage detection on small order. So we have taken the maximum we were able to do in a reasonable time. So we have done it on 4 shares. And what we want to do with this leakage detection is to extract potential risk factor, which could come from the share recombination. And we want to extrapolate the security from the 4 share case to the 32 shares case. So we have launched a t-test on our 4 shares implementation. So in the upper part, you have the power consumption of the icebox. And on the lower parts, you have the t-test at order 4. So with 4 share, we have what we expected. That is some leakages. And more interestingly, if we look at the lower orders, so order 1, 2, and 3, we didn't spot anything that could lead to think there is some kind of share recombination. So from now, we'll just assume that there is no share recombination. And now we want to look at the noisy leakage model. So what we want to do here is to compute the hypothetical mutual information in function of your noise, so the SNR. So we measure the SNR of our device thanks to linear regression. And even though we didn't spot anything that could show a flaw in the security, we still, in order to be very conservative and to have some worst-case security level, we still consider it. So for the 32-1 order security, so when there is no flaw with the share recombination, we see that we have a security which is beyond than 2 to the 188. And even when we have some flow appearing that is for the 15 case security, we have something which is still beyond to the 64, so which is something quite nice. And we have also looked at another kind of adversary which can exploit the fact that you have repetition of your encoding at some point, and so this repetition you can use it to do averaging and reduce the noise in this. And so the numbers are just coming from the fact that in our code some value was repeated 6 times at max. And here we see that of course the security is decreasing. Now if we want to put things together, so here we have the measurement complexity of GIS at order 31 and GIS at order 15 in different scenarios of adversary. So the first one is the single tuple adversary, so just the one we saw at the slide before. But we have also taken into account an adversary which is able to exploit all the information in all tuples of the computation. So it's essentially what do horizontal side-channel attacks. And also, we have taken what we call the worst case security, which is an adversary which is able to exploit all tuples, plus the possibility that these tuples are repeated a certain number of times, and you can average them and reduce the noise in it. And from this figure, we can nicely see that we have some kind of order reduction. So the vertical line are showing the order reduction, which is coming from the security flow with spot thanks to the leakage regression from the detection tools. And horizontally, we have order reduction which is coming from the noise and from the potential averaging. So even in the case of the worst case adversary, we are still with some kind of quite good security. We are under the 2240 for the 15 order case and under upper, and we are better than 2284 for the 31 security case. So I will conclude my talk. So in conclusion, we have implemented a very high order masking scheme. So and we have done it and show that it's not out of reach. We can do it in reasonable clock cycles. So we manipulated 32 shares. We introduced, in order to try to evaluate such a scheme, the multimodal approach, which can give us some kind of security level for something very high order. All this model is based on falsifiable assumption. And as open problem, so in terms of the implementation, we have not looked at the case when the size of the register is different from the number of shares. So potentially there is something here to do because the rotation will not be for free. So we have to look at that. So something also open, but maybe very hard to do, is make a full code analysis to reduce the number of refreshing and reduce the number of randomness. And so we have also the problem of the averaging. So one solution to avoid the refreshing, the averaging adversary is just to put refresh everywhere, but it's very costly. So maybe we can think at a better representation of the S-box in order to reduce the repetition of some value. So thank you for your attention.
Thank you very much. Are there questions? Do I see any questions? There's a question over there. Ah, okay. Thanks.
Yes, thank you for your presentation. I have a question about the importance of crosstalk. Do you have any thought about, for example, when you increase the number of shares from 4 to 32, for example,
yeah.
And if you implement it on, I don't know, like FPGA, then a lot of these shares will be combined together, and then there will be a lot of crosstalk. Do you have any thought about that? Or?
On FPGA, I have absolutely no clue about how it will work, but on software, apparently, there is no problem from that because you have only the 4 shares on your register, But maybe on FPGA it could be an issue, yeah. But I don't know about it.
Okay. Yeah, thank you.
I don't see more questions, but I have questions. So your cycle count that you showed, maybe I didn't get this, but did that include the cycles required for randomness generation for refreshing?
Yeah, everything.
Okay. How did you generate the randomness for the refreshing?
With a PRNG.
So they just call the systems?
Yeah,
okay.
Exactly.
And then, I mean, basically what you're doing is you're doing a bit-sliced implementation where the degree of parallelism just comes from the number of shares.
Yeah, exactly.
So this is completely generic. So in principle, it should be possible.
No, it's not generic. It's just we are fixed to the number of to the size of the register.
True, but generic in the sense that you can apply this to any algorithm.
Ah, yeah, okay.
So in principle, it should be possible to just write like a gate-level description of an algorithm, run a compiler over it, and this just magically appears this kind of implementation, right?
I guess so, yeah.
Okay. But no such compiler exists at the moment?
No.
Okay. Any more questions? If not, then please join me in thanking Anthony again. While the speaker is getting set up, it's my pleasure to introduce the next speaker, Tiago Reis, who presents joint work with Diego Aranha and Julio López. And it's present runs fast, efficient and secure implementation in software. Please.
How does this work? Oh, okay, thank you. Oh, so thank you for the introduction. And so I'm starting my talk. As soon as I can pass the slide. Okay. Yeah. Oh, okay, now it's working. So as we all know, lightweight crypto is now on the rise, and we constantly see many new designs appearing all the time and being analyzed. But it turns out that it might be useful also to take a look on older designs, especially when these older designs have already taken a lot of cryptanalytic attention, and we now are more confident about their claims of security, which is exactly the case of the present block cipher, which is the subject of our work. It's also important to notice that efficiency is the main goal of our implementation here, but we take care about good practices towards mitigating side channel attacks. For example, our implementations are always in constant time. So let's first describe the present block cipher as have originally been proposed. Its design has been shown in CHES 2007, so 10 years ago, by Bogdanov et al. And it was claimed to be an ultra-lightweight block cipher, and it has two versions, one with 80-bit key and one with 128-bit key. They both operate on a 64-bit block, and these two versions only differ by their key schedule. The substitution boxes are the same, the permutations are the same, just the pre-calculation of the round keys is different. So it's a substitution permutation network, a very straightforward one. At each round, you just sum the subkeys, then each 4 consecutive bits undergo a substitution box, and then all the bits are permutated. This bit permutation are not trivial to be implemented in software, hence it has always been regarded as a cipher to be implemented in hardware. Here is a pseudocode showing that first you generate all the subkeys or the round keys to the key schedule. Then for each round, you sum the subkeys, go through the substitution boxes, and then permutate the bits. Here is the S box. It's a 4-bit to 4-bit X box, so it's a small one. In principle, it's pretty safe to assume that it can be implemented as a lookup table without incurring in the danger of suffering cache timing attack, because it's such a small table. But of course, it can be implemented as a set of Boolean formulas to simulate this S box. And actually, we will use these formulas in our work. Now let's see the first interesting part, the permutation of present. The permutation P of present takes the ith bit to the position Pi as described by this equation. Here we show the 64 bits of the state and how they are moved by the permutation after it's applied. And the state is not organized this way by chance. We actually implement like this, as 4 registers with 16 bits. And it will be clear why shortly. First, let's analyze what this permutation is doing. The first 4 bits go to the first column when the permutation is applied. Then the next 4 bits also go to the second column. And then the next 4 bits go to the third column, and so on. So we will say that this state is bit sliced because all of its 4 consecutive bits here on the original state are taken into columns of the permuted state. And now, how people usually implement present in software? Well, we already said that it's regarded as a hardware-based block cipher, but, well, people definitely implemented it in software. Searching throughout public repositories and published work, we noticed 2 main strategies. First one is by using large lookup tables, maybe to perform several lookup to the S box at once, or maybe to merge a part of the S box with the permutation and then to simplify the permutation afterwards. Or another totally different way is by bit slicing. This first strategy is not very good when you regard side channel attacks, for example, or in processors where you have cache memory, because you are using very large tables. And also, even if you don't have cache memory, when you use very large tables, you are deviating from the main purpose of the lightweight cryptography, which is to consume few resources. And the second way, bit slicing, usually provides efficient implementations, but has limited applications. Because you usually require to have a large amount of data to encrypt or decrypt for it to be efficient. For example, if you have 2 blocks or 1 block of data to be encrypted using a bit slice implementation, your performance will be terrible. And our proposal kind of meets these 2 strategies in the middle. And shortly we will see why. But first, we will interchange the permutations in test boxes, and then we'll rework the permutations for them to be more software friendly. So first, we will see how we interchange permutations in test boxes. First, the original design of present, we first, at each round, we first applied S boxes for each of 4 consecutive bits of the state, and then we apply the permutation, changing these 4 consecutive bits into columns of the state. That's what we have seen before. And what we're proposing is, first we will permutate the state, and then we will apply the S box not over 4 consecutive bits in a row, but over 4 column consecutive bits. So that, and this S-box now can be efficiently applied as those Boolean formulas, because you can do the Boolean formulas for all the 16 S-boxes at once. So now we'll see a scheme that shows the whole idea of our proposal. First, in the subfigure A, we have the original proposal. We sum the subkeys, and then we apply the S-box, and then permutation, and then we repeat. This is like the 2 consecutive rounds of present, rounds I and I+1. Then, first thing we said we can do is to swap S-box and permutation, as long as we now compute the S-box over the columns of the state. We call this S-box BS. So this is subfigure B. Now, towards subfigure C, the only thing we do is to shift the sum of the subkey to after the permutation. And of course we can do it because the permutation is additive. So now we have a more subtle step. First, let me comment that this is clearly a downside, because now we are applying another permutation, but we will address this issue real quickly. But then the next step towards subfigure D is maybe more subtle, but we will change it. Instead of applying 2 permutations P, we will apply 2 different permutations, P0 and P1. So at first glance, we notice that, of course, applying P0 and then P1 has to have the same effect as applying P and then P. So P0, applying P0 and then applying P1 has to be the same as applying P squared. And furthermore, there has to be another property regarding these permutations, is that P0 prepares the state to undergo this substitution box as well. So it has to bit slice the state in the same way that P did. But as long as we attend to these 2 requirements, P0 and P1 are equivalent to P and P in these schemes. So we can convert all this all the way from subfigure A, which is the original proposal, to what we propose, which is the subfigure D. Here is the pseudocode representing exactly what is shown in the scheme. And now, just for illustration, what happens with the 64 bits of the state when they undergo P0 or P1. Notice that, in fact, P0 does bit slice the state. Every column consists of 4 consecutive bits. And then P1 doesn't have any very special property. It's just used to correct the state and restore it to a state which is equivalent to the original one. So that's what I said. SBS is the S-box calculated in a bit-sliced fashion. Both S-boxes are calculated over bit-sliced fashion very efficiently with Boolean formulas, 16 S-boxes in parallel. And permutations P0 and P1 show some interesting properties. The first interesting property is that they are very software-friendly. We obtain P0 and P1 so that they can be implemented in 16 clock cycles using ARM instructions, whereas P requires 28 cycles. And furthermore, other properties are shown here. Of course, P1 composed with P0 has to be P squared, otherwise our formulation wouldn't be equivalent to the original formulation. And we have some other nice properties. For example, P0 and P1 are involutory. They are their own inverses, and that's important, for example, when you are implementing the decryption algorithm, because, well, we're saying that our encryption is more efficient when we implement this way, but maybe it would ruin decryption and made it much worse. but actually it doesn't happen because the permutations on the encryption are exactly P0 and P1 again, because they are their own inverses. And now what I had commented about the downside is that the key schedule undergoes one extra permutation every 2 rounds, as we can see in the scheme before. Now every 2 rounds we have an extra permutation P here on the key schedule. But it's not a very serious problem, because typically what happens is that we do not encrypt just one block for every key we use. We typically encrypt many blocks after we use one key. So we can just pre-compute all the round keys and do this permutation on the pre-processing phase, and we can just use this pre-computed value here with just being a sum. So this downside is not very serious as long as we encrypt several blocks with the same key. And this technique can be generalized. For present, it's very convenient. The permutations have very special properties, but the technique can be generalized. As long as we have a substitution permutation network that goes like present, so using S boxes over consecutive bits and going through all the state and then performing bit permutations. One such example is the gift, which was presented yesterday, and the same technique can be applied to that algorithm. Of course, depending on the original permutations, it might not render a performance improvement because, well, the modified permutations could turn out to be worse than the original ones, which is not what happens with present, but maybe for a certain design it would happen. But the upside is that the S-box can always be computed efficiently and isochronously. That is actually why we used the technique in the first place, to compute the S-boxes as Boolean formulas all in parallel. So here is the scheme for the generalized technique. If we have a substitution permutation network that works like this, the S-box is applied over all the state, and then a permutation, a general permutation P prime, and then you sum the round key and repeat this for many rounds. You can use different permutations, P0 prime, P1 prime, and P2 prime, to decompose this permutation in order to compute the S boxes in a more efficient form. First thing to comment is that when we implement present, this permutation here turns out to be the identity permutation. So for present, we only have P0 and P1, but in general, we might have to apply a final permutation to get things back to their original places. But notice that this is not an extra permutation when you're actually running the algorithm, because when you repeat this block several times, what you actually compute is a composition between P2 prime and P0 prime, so it ends up being only one permutation again. So every 2 rounds, we have to compute 2 permutations. Here is a description of how you can generate these permutations here, P0, P1, and P2. And now, regarding present, once again, our specific subject of study, we have some implementation results to show. First, our target architecture was ARM processors, mainly Cortex-M and Cortex-A processors, and we used the scenarios proposed by the Felix framework in order to provide a fair comparison with the literature. So depending on the mode of operation used, CBC or CTR, we can encrypt up to 2 blocks in parallel when we are working on 32-bit architecture. Why? Well, because if you remember well, our registers only use 16 bits. So we have, if we're on 32-bit architecture, we are wasting 16 bits on each register, so we can just use that to encrypt another block in parallel. And using the same rationale for 64-bit, we can encrypt 4 blocks. And for those processors that are capable of using ARM Neon instructions, we can encrypt up to 8 blocks in parallel. And we achieved very relevant speed up over the literature results. And remember, this, when I say that it depends on the mode used, it's because the CBC mode does not allow parallel encryption. Here is the figure to remember that when you encrypt several blocks, several consecutive blocks, there is a dependence over the output of one block and the input of the next block when you're encrypting in CBC. The decryption can be done in parallel, and for CTR, everything is good. We can parallelize everything. So the optimal results for us will be when we use CTR. Our results for CBC are not bad, but here is our best results that are for the scenario where we encrypt 128 bits under CTR mode, assuming we already pre-computed the subkeys, which is a scenario proposed by the Felix framework. Here we have our numbers for code size and execution time. And if we compare to Dino et al.'s work, which is when the Felix framework is proposed, we notice that our execution time is almost 8 times better, and still we have a code size that is a bit smaller. Also, another comparison that is convenient to do is with other popular block ciphers, which is the case of the AES, and if we compare it with Schwabe and Stoffelin's implementation, we notice that our execution time is on par, at least on Cortex-M4, with their implementation of AES, but we have a much smaller code footprint. And we also have implementations in Neon and a masked implementation that also show good results. Please refer to the paper if you want to know the exact numbers. And then we can conclude our work, saying that we devised a method that implements certain kinds of substitution permutation networks and that can provide substitution substantial performance improvements. For present specifically, we were able to achieve a factor close to 8 compared to state-of-the-art results. And also, using our technique, present becomes somewhat competitive with widely used block ciphers such as the AES. And just as an acknowledgement, we would like to thank the LG Electronics for funding the research, and also thank you all for your attention.
Are there questions for Tiago?
A non-technical one. Does LG Electronic has bought and patented your IP here?
I'm sorry?
So are the software implementation techniques here covered by patents?
Not yet, but it might become.
Okay, any other questions? Maybe an obvious question to ask somewhat in the same direction, is the code available?
Yeah, for the same reason, not exactly. Yes, we do not have the full code available, but if you refer to the paper, you can see that we have the code for the permutations and the S boxes, which are the building blocks, and one could easily reproduce the code when you have the codes for the substitution box and the permutations.
Okay. I don't see. There's one question there.
Thank you for the talk. Did you make also the comparison with spec algorithm?
Well, not formally. If I recall correctly, spec is still quite more efficient, but well, present has its advantages. It's more well known. It has undergone more study and more cryptanalytical attention by now, and spec is a somewhat more recent design, and well, that's it. But yes, spec is better regarding software performance.
Any more questions? If not, there's one.
I have one tiny question. According to your implementation, since you have to save all the run key right before the real calculation, so the storage for the keys also the error is also included in your gate count.
Yes. The numbers include the key schedule, processing and storage of the keys.
Okay. Any more questions? If not, then please join me in thanking Tiago again. And then it's my pleasure to introduce the next speaker, Geovandro Pereira, who will be presenting joint work with Julio, Patrick Longa, Oscar Reparaz, and Hwajeong Seo. And he will be speaking on FourQ on embedded devices with strong countermeasures against side channel attacks. Please.
Thank you for the introduction, Peter. So this is a joint work with Julio, Patrick Longa, Oscar Reparaz, and Hwajeong Seo. And it talks about safe and fast implementation for embedded devices for the FourQ curve. Okay, so I want to start with motivation for our work. So in '96, Kocher introduced side channel analysis attacks and against implementations, crypto implementations. And 3 years later, these attacks were extended for differential power analysis. So around the same time, NIST published the 15 popular NIST curves. And if you look at the standards, they didn't take into account these new attacks by Kocher in the design of these new curves. So these new attacks imposed new restrictions, new requirements for designing good elliptic curves, including constant time algorithms. And at that time, NIST used a model of Weierstrass curves, which doesn't have complete formulas, didn't have complete formulas at that time. So there's another model that had complete formulas, no exceptions. When you want to add like a 0 point or a non-zero point, these formulas always run in constant time. So also another interesting new requirement after Edward Snowden's revelations about NSA and backdoors is that we want to understand the provenance of the new elliptic curves. How do you build the curves that you prevent against or try to minimize against backdoors? And NIST is aware of that, about these new restrictions. So in 2015, they promoted a workshop about new generation elliptic curves. And some authors in that workshop pointed out that the main motivation to come up with new curves is better performance and side channel resistance. So for that, thinking about that, this is the curve we selected for our work, which is the FourQ proposed in 2015 by Longa and Costello. And this curve looks very promising. We have some previous works with nice speedups compared with popular curves like curve 25519. And these speedups range from 1.9 times up to 3 times, depending on the platform you are implementing. And here there's a range in this row for the Cortex M4. Because some implementers reported that depending on the manufacturer that is building the architecture, you could get different performance results. So, but still, we have nice speedups for the range. They got some results. So this is the curve equation for FourQ. It is a twisted Edwards curve defined over fp squared, where p is Mersenne prime, which is a really nice prime. We can do fast arithmetic using Mersenne primes, like doing modular reduction. And it's not a prime order elliptic curve as any other twisted Edwards curve. So usually we work with a prime order subgroup N. There's always a cofactor. And in this case, the cofactor is 392. And this curve, as I said, is under the twisted Edwards model, which provides complete formulas. And there is a special feature for this curve, which is that it is endowed with 2 efficient endomorphisms, psi and phi. There are 2 techniques that allow it to come up with these 2 endomorphisms. And this means that having these 2 endomorphisms allows you to compute small multiples of points faster. So if you have a large scalar m, you want to multiply by a point p, you could decompose this scalar m as a linear combination of the point p and the evaluation of the endomorphisms on p. So here we have a 4 decomposition, which was introduced in the original FourQ paper. And usually you have a scalar of size 256 bits, and we could decompose it into small scalars of size 64 bits. And here is just an example of a large scalar m and the decomposition. We can always find this decomposition for every m. They proved that in the paper. And here's an example of this decomposition. And there's another nice result in the paper, which is a signed representation for these smaller scalars. And they proved also that we could also get a property called sign aligning. So if you align the same position of the bits of the small scalars and you look at the columns, the sign of the coefficients A2 up to A4 will be the same sign of the coefficient A1. So this will allow us to do some optimizations later. I will talk about this. And we can always find this decomposition. So here is a representation of this signed version with a sign and absolute value or a modulus of this 3-bit digit and then a sign. So here is how we can use this property to speed up a scalar multiplication. We look at those digits, 3-bit digits with a sign. we need actually 8 points for the table. Usually we would need 16 points for 4 bits, but here we can use just 8 points because of this property. And this is how the scalar multiplication runs. We always start computing a point Q, and we look at the first digit. We index the table, T of 6 in this case, and then we start the main loop for the scalar multiplication. We always double Q, and we look at the next sign of the next digit, which is minus in here, and then again the next digit is 6. So we run this for every digit, and everyone can see that we always run a same amount of times. We always have 64 doublings and 64 additions or subtractions. So this helps to protect against simple power analysis because we have constant time scalar multiplication. So, and also, as I mentioned, we have a smaller table to use and multiply the scalars. And I mentioned how to protect against against simple power analysis. So we have complete formulas due to the twisted adders model, and then we have a regular double and add algorithm, as I showed before. So this is okay. Now we need to talk about more powerful attacks like differential power analysis and countermeasures. Initially, Coron suggested 4 countermeasures for those kinds of more powerful attacks. The first one is scalar multiplication, scalar randomization, where instead of multiplying your point P by the scalar M, we mask the scalar with a random multiple of the curve order. So this is always true because this equality is always true because when you multiply P by the curve order, we always get 0 since the order of P divides the order of the curve. So the next countermeasure is point blinding, where instead of blinding the coefficient, the scalar, we are blinding the point to be multiplied by. And we generate a point R, a random point R. This was inspired in the original Chang's blind signatures. So after blinding the point, then we conduct the scalar multiplication with the blinded point, and then at the end we need to unblind the point. So we need to start these 2 points R and M times R. If you consider that you are using this secret many times. So we could start these 2 points, and also it's good to make R unpredictable, and then there's an update function for R. Every time you do a scalar multiplication, you update R by multiplying it by 2 times minus 1 to the random bit B. And the third countermeasure for this operation is projective coordinate randomization. So we could always randomize these coordinates of the point P by multiplying by a random coefficient lambda. If lambda is non-zero, this point will always be a point P. It's just a scaling of the point. In projective coordinates, we have the same point. So this was the third countermeasure suggested by Coron. And let's look at the first one in our context. So it's suggested to randomize the scalar, where the randomization element R would be a small element, like 20 bits. But it turns out that for many elliptic curves defined over some primes, like additions of powers of 2 plus some small coefficient C, the order of the curve has some repetitions of 1s and 0s. So when you multiply the order of the curve by a small element, we just shift these patterns, and then you add to the message. Actually, you are leaking some bits of the message, which is not good. In this example, this is exactly the order of the curve P to 256 by NIST. So In the case of FourQ, actually this problem doesn't happen because, in fact, the order of the curve has some patterns, but since you work with the prime order subgroup n, and you compute n, you look at its representation, we don't have such a pattern. So in here, we could apply this technique without worrying about this patterns leaking. And, but can we do better? Because I showed you that for FourQ, we can decompose the big scalar into smaller scalars. So a question is, can you do better than this? And the answer is yes. And how? I'll show how next. So as I mentioned, Couron's method is not the best one for curves endowed with endomorphisms. And in FourQ, actually there's a better technique introduced by Standaert et al. In 2003. I think it was in CHES. And it applies for curves who have some efficient endomorphism using this technique to compute endomorphisms. And it turns out that our curve has this kind of endomorphisms and one more. And then we extended this technique for 2 endomorphisms, which decompose a scalar into 4 mini-scalars instead of 2 mini-scalars as in this work. So this is one contribution. And I mentioned that the mini-scalars were 64-bit each. Introducing this countermeasure, they will increase by 16-bit. So then the main loop of the scalar multiplication will increase by a little bit, not much. And we can still have not a full order loop, still a small loop. And we do not need to worry about patterns of repetitions. And the overhead in here would be 25%. So if you use, introduce some countermeasures in other curves that do not have these endomorphisms, the overhead to include this countermeasure would be a little higher. So here is the main algorithm, the protected scalar multiplication. So I will just highlight the main points of the algorithm where we are introducing the countermeasures. So here, at this point, we are always updating the blinding point R. Actually, instead of multiplying by 2 in here, as suggested in the original paper, we are multiplying by 3 to avoid some correlation attacks. And we always do this. And also, to compute that table I mentioned in the beginning, now we need to blind the table as well with R. So it turns out that we do not have this nice property of sign alignment anymore. But so in this case, the table is the usual table size, which is 16 points. And the last technique to randomize the point coordinate, the projective point coordinates, we received 82 masks in FP here, and then we randomize all the points, R and P here, and all the points in the main loop S in here. So this is the projective coordinate randomization that I mentioned before. And also, this is the new the technique we introduced that expands Standaert et al. To randomize the multiscalar. We proved that we can always have this representation, the expanded representation of 80 bits for each mini-scalar in here. It's proposition 1 of the paper. The proof for this proposition is in the extended version of the paper. It's not in the current version. Which is available already. And as I said, we have to increase these mini-scalars by 16 bits. So 64 plus 16, we have 80 iterations in the main loop, which is, has some penalty, but is not that much. So with respect to side channel evaluation, practical experiments, so we have evaluated the implementation for ARM. M4. So this model has low noise, meaning that you can just conduct a few number of experiments and measurements and have a few number of traces, and we could have some some nice results recovering the keys if you don't use any countermeasure. And we performed some leakage detection tests by not using any countermeasure. We started with this, and then we introduced a countermeasure and tried to find some correlation and compared with the countermeasure for every countermeasure. And then we activated all of them and also tried to come up with the leakage and extract some bits, but up to 10 million traces we couldn't extract any information when all the countermeasures were activated. So here is one example in the paper for point blinding. So on the left, we don't have any countermeasure activated, and we target a specific case where there was no point blinding. We are trying to recover a bit. And in fact, we found a peak in here. And when we added point blinding countermeasure, we can see that there was no correlation detected for a first order correlation. And with respect to our library, so it's an open source library. As far as we know, it's the first open source library with that many amount of countermeasures for scalar multiplication. So it's under low restrictive license, MIT license. So it's implemented in C language and assembly. It's optional. You can use or not for every one of these 3 devices. And it's highly customizable in the sense that you could, at compilation time, select if you want or not to use the endomorphisms. This is a trade-off between space and time. You could also use this trade-off for the table sizes, and the same thing for assembly. And we also implemented elliptic curve Diffie-Hellman with and without key compression as crypto primitives. And recently, we included the FourQ signature, which is a signature based on FourQ curve in our library, and it's in the extended version of the paper as well. And this library set new speed records for all these primitives in these 3 devices. And it's available. The link is actually in the paper. I forgot to put the link in here, but you can find the link for all the libraries in the paper. And here are the speed record results that I mentioned. For the 3 platforms and for different operations like fixed-based scalar multiplication, random scalar multiplication, and Diffie-Hellman static and ephemeral. So I just want to highlight some interesting points here. It's a previous implementation by Hennes in CHES last year. So we got a speed up of about 1.9 times in the 80 mega device. And for the comparison with the curve 25519, there's a result in 2015 by Du et al. And we got 2.8 speed up in AVR, 2.5 speed up in MSP, and a nice speed up in ARM of 3.9 times faster ephemeral Diffie-Hellman computation. And some remarks and future work. We provided a fast and secure software implementation of the FourQ curve for 3 embedded devices. We also provided a proof of concept, including a library, an open source library with side channel resistance and evaluation. Just a disclaimer, this does not mean that we won't have attacks against our implementation. That might be the case that new attacks come up, and this is just a disclaimer to say that this is not 100% safe. And also we focused on speed for all implementations. So one future work would be try to come up with better memory trade-offs, try to minimize memory in all settings. And also would be interesting to evaluate our implementation in different languages and platforms like JavaScript, Rust, and some other embedded platforms. So with that, I conclude my talk. Thanks for your attention.
Thank you very much. There's already several questions. I'll run around and you do there? Okay.
You go back to the FFFFF slide.
Sorry?
There was a slide where you had all the Fs on it for the top half of the bits all being Fs. I mean, basically adding nothing in the top bits. The cron countermeasure where you're adding in particular multiple of the order.
You mentioned, okay.
This one.
Yeah.
This one?
Yeah. So
here we are not using this countermeasure actually.
yeah, I understand that, but I was wondering about your statement that it's safe to use this multiples of the number down below. Because if I understand correctly, that number down below, if you multiply it by 392, then you get the dangerous number up above, which means that you only have 392 different multiples that are modifying the top half of the bits. So there's going to be 392 different classes of randomizations, and then you have to check for, I mean, basically you classify the different samples into 392 categories.
Yeah, that's an interesting point. Fortunately, we didn't use this countermeasure, but it seems that your reasoning is correct.
You did a nice work on side channel protection. Did you consider fault attacks, especially safe error attacks?
No, we just focused on passive attacks, not active attacks. So we didn't try to protect against this kind of.
Do you plan future work on that, especially securing the table lookup?
Yeah, maybe. Yeah. I forgot to mention as a future work, but of course this is should be included.
Okay, while I don't see other questions, I have a question actually following up on the table lookup. So how exactly do you do the table lookup? Do you actually access memory at a secret location, or do you load the whole table and then use arithmetic to pick the result that you want?
We load the whole table. There's no secret masking in the indexes, but many other works, they assume that as well. So they say that they couldn't detect any leakage by doing that. So that's why we followed this trend.
So the trend of accessing at secret location or loading the whole table?
The whole table.
Okay,
Yeah.
but then
the table is small, right?
yeah, but then I mean, when you load the whole table, you're then basically masking out the one that you really want. Did you try templating that mask?
No.
I mean, at some point you basically say, well, if I'm at the right position, then pick that one, which when you do it through arithmetic, you do it typically through masking with either all ones or all zeros, which is something that you can very easily template. So that might be something interesting to look into. It might actually leak less if you access at a secret location.
Yeah, I see. Template attacks are like one of the most powerful attacks, right? So we focused more on differential attacks.
Okay.
But I agree with you.
Okay. Any more questions? If not, then please join me in thanking Geovandro again.
Okay, thank you.
And then we come to the last talk of this session and the last talk of CHES 2017. And it's my pleasure to introduce the speaker, Amir Moradi. And that's joint work with Jérémy Jean, Thomas Peyrin, and Pascal Sasdrich. And he will be speaking on bit sliding. I'm curious what that is.
Thank you so much. Yeah, let's see why I'm here. I'm trying to use, okay. I try to use actually here, you see, on all the screens. Good. let's see what is the story and actually why we have done this work. It's indeed motivated by design of Catan and Simon bit serial implementations. Catan is a nonlinear LFSR or a stream-based block cipher, symmetric block cipher, and its architecture actually was borrowed from keylog. The keylog you see here at the right side, that the key is in a register with 64-bit, and also the plaintext or state of the cipher 32-bit, and then every clock cycle, just one bit is updated, but everything is shifted to the right. And then this design was broken, and then based on that, let's say, construction and idea, the other cipher Catan was defined or developed, which actually follows the same construction, means that every clock cycle, just one bit is updated, or a couple of bits are updated, and everything is shifted. In case of Simon and a spec, for instance, in Simon, it's a Faisal architecture, and actually it allows bit serial architecture again, means that again, every clock cycle, just one bit is updated and everything is shifted. And it also allows a scalable architecture. It means that not only one bit shifting, it's 2-bit shifting is possible, 4-bit shifting possible, and so on. It gave a lot of freedom in implementation, means that you could have a very good trade-off between the latency and also the area. You could decrease the area very much, but of course at the cost of the latency. And then we have actually thought about how about the SPN constructions, substitution permutation networks. Means that you have here the key schedule, which gives you the key, and then at every round you have the, most of the time, key addition, and then substitution networks with the subparters, and then permutation, which plays the role of the diffusion, and then again subkey, and so on. This round or this architecture is repeated a couple of times till the ciphertext is ready. And then we want to check whether this is possible also for SPN constructions, because up to now it was only possible for a stream cipher construction or stream cipher based construction, or based on only the Simon or spec. If we look at the trade-offs for SPN implementations, we have the designs like fully unrolled, means that everything is in combinatorial. Combinatorial logic means you give just a plain text, and then at the end, after a couple of let's say nanoseconds, you get the ciphertext out without any clock. It's completely clockless. Or you have the pipeline architecture, means that you put a register between the rounds of the cipher, and then you increase the throughput. But of course, you have a bit higher area, but you increase the throughput, but with the price of the latency. And you have a round-based architecture, because as I said, SPN constructions usually follow a round architecture, and then you have one round, and every clock cycle, just one round is updated. Or you have a serialized architecture. Yeah, but this serial architecture is actually limited to the size of the S-box. First of all, here, if you go from this way, from fully unrolled to serial, as I said, your latency is higher. And also from the other side, if you come from serial to fully unrolled, your area is getting higher. I mean, when you want to have a very low footprint implementation, then you select a serial implementation, and which is actually the target of most of the lightweight cryptography or lightweight crypto algorithm which have been proposed till now. They actually follow S-bit SPOX and L-bit linear function, and the S-bit SPOX forces us to do serialization based on S-bit. Means that if you have a present LED, Klein, or something else which has a 4-bit SPOX, then you are restricted to Nibble-based implementations. And if you consider AES, then the smallest one, the smallest serialized architecture, which is known up to now, is 8-bit bits or 8-bit serial architecture. But also then the diffusion layer is L-bit linear, or let's say L-bit linear function. It's also usually a multiple of S-bits. For instance, for AES, you have 8-bit SPOX, and you have mixed column, which works on 4 bytes. Means that again, L is 32, which is a factor of 8 of a size of the SPOX. What is also done in most of the implementation of the lightweight cryptography up to now in the smallest footprint is the use of the scan flip-flops. First of all, what is a scan flip-flop? Scan flip-flop is made by a flip-flop and a multiplexer. It was developed not particularly for lightweight cryptography. It was developed many years ago for testing purposes. Means that when you want to have the test in your system, you want to change the input of this flip-flop to give your manual input instead of the output of the function, then you use these scan flip-flops to make a scan chain in whole of the circuit for testing purposes. The point here is why is many times the scan flip-flops are used in implementation of the ciphers with a small footprints is that the size of the scan flip-flop is usually very optimized and is smaller than if you have a D flip-flop plus a multiplexer. For instance, here we have considered 5 different process or libraries, process technologies, from IBM 130 to NAND gate, and also use UMC 90, 130, and 180. You see here the scan flip-flops, of course, is obviously larger than the normal D flip-flop, but if you add the size of the multiplexer, which is roughly 2.3 gate equivalents, to the size of the D flip-flop, it's most of the time larger than the size of the scan flip-flop. That is motivated using a scan flip-flop. Here is this schematic of the smallest known serial architecture of the AES, which is known as Atomic AES version 2. What you can see here at the left side is a state registers, means that you have here 16 state registers, each of them 8-bit, 1 byte. The gray one are the scan flip-flops, means that you have here 8-bit multiplied by 3, I mean 3 times 8-bit scan flip-flops, and here for the key scheduling you have also 8 times 8-bit scan flip-flops, and then everything here is shifted to the left from right to left to the state, and then the key scheduling actually does the same, but for doing the particular parts of the key schedule, it has to also shift in vertical direction. For that reason, they need to employ the scan flip-flops. This architecture supports encryption and decryption, and also it uses clock gating for each row. Let me get back here. To implement the shift rows, the first row should be a stop, the second row should be shifted once, the third row 2 times, and the last row 3 times should be shifted to the left. For that reason, they use the clock gating, means that they stop the clock for those particular rounds. I have a problem here. It doesn't go stopped somehow. It doesn't react to the mouse. It doesn't react to the keyboard. Ah, it works now. Okay. In total, 88 scan flip-flop is used in this design. And another contribution that they had was that the mixed column inverse is implemented by 3 times applying the mixed column. And then it actually allows you to avoid an area that you need to mix column inverse. Just repeat operation of the mixed column 3 times, and you have the mixed column inverse. They use also the CANRIDE SPOX, which is a pretty well-known design for the SPOX, which supports both SPOX and SPOX inverse. In total, they reported 2,060 gate equivalents using the ST Microelectronics 90 nanometer technology library, 246 clock sockets for encryption, and 326 clock sockets for decryption. That this difference between these numbers is coming from the mixed column inverse, which you have to apply mixed column 3 times. Then now, what is a bit of slicing? We want to use as many as possible regular flip-flops and use as less as possible scan flip-flops. Means that almost all registers register cells always shift without any enable signal, without any clock gating, which can be implemented by normal D flip-flop, regular D flip-flop, which is the smallest without any enable. And also, a few of them should be definitely with a scan flip-flop, means that the input should be routed differently, should be selected from different sources. The first challenge is how to implement S-bit SPOX in a serial way. For instance, it might be easy for Piccolo and Skinny SPOXes. For instance, here you see the design of the Skinny SPOX, which has actually a iterative architecture. You can just implement this part, which updates only 1 bit, and the other bits are just shifted. Or, but in case of AES or present SPOXes, for instance, up to now we don't have any solution to implement them in serial way, but of course we can consider them in the parallel. But as a comment, I can say that if you have spent some time in a poster session, there is a session from Leuven, Carl Leuven, that how to serially implement the AES box. It might be useful in this architecture. But what we have done is just completely parallel implementation of the S-box that I will explain later. The second challenge is actually the permutation. How do we implement a permutation or diffusion layer serially? It's mainly ad hoc, and I will explain more mainly about the AES, but it's hard for other, for instance, for present. We will see why. First of all, how the box serialization in parallel works. Suppose here you have the scan flip-flops here. The input is shifted, for instance, in case of the AES, 7 times, 7 clock cycles. And then in one clock cycle, when the input is available at the S-box, then the input is not given to the flip-flop here, scan flip-flop, but the output of S-box is given here. And then after 8 clock cycles, you have full S-box in the design. Of course, this is a straightforward implementation of parallel, means that the input is just shifted 7 times, and then the 8 clock cycle, the S-box output is realized. Here is the bit serial architecture or bit serial architecture of the AES-128, an encryption-only functionality. This is a bit hard to understand at the start, but what I need to explain is that we have only 20 scan flip-flops, only those that they are dark here, the dark gray ones. The S-box works here, as I explained. And what is important is that there is no clock gating and there is no enable signal. It means that all of the time, without any control, all these flops are just clocked and triggered and they are shifting. Those that they are white, they are just shifting to the left, no control at all. But those that they are gray, they are scan flip-flops and that their input is selected. How it works, explain it shortly. First 128 clock cycles, the plaintext and the key are loaded serially, means that here the plaintext is going here and then to the next row till here, 128 clock cycles. And then the next 120 clock cycles, the add round key and subbytes are realized. Means that here the key bits are also provided serially. The output, which is here 1 bit, again is going through here the multiplexers. And as I explained, 7 clock cycles, the output of the XOR add round key are going there, and then in the 8 clock cycle, the output of the S-box is written in the register. Then in total, 128 clock cycles we need for the add round key and the sub key for the first round. And then the shift rows is also implemented in 8 clock cycles. Means that here, if you see, here there are scan flip-flops that define whether you have which input is coming through the register. The blue lines are actually realizing, if it's seeable, yeah. The blue lines actually are realizing the shift rows. Then 8 clock cycle we have for the shift rows, and then the mix column is also fully in serial. How does it work? We have here 8 XOR gates and 8 NAND gates. The thing is, we have also a couple of registers here. 4 registers that you see here, that the green registers are required for the extra addition that you need to apply for the multiply by 2. The mix column is just multiply by 2 and multiply by 3 and XOR. And then the multiply by 2, whether based on the MSB of the every byte, you decide whether you do the extra addition or not, or then you add the polynomial constant to this. These registers are required for that to save this. In the last clock cycle of the shift rows, the last bit is also saved in these green registers, and they define whether we have the extra addition or not. And then it goes through the network of these gates to give 4-bit output of the mix column. And then every clock cycle, 4 output bits of the mix column are ready and will be stored in this column. Means that in 32 clock cycles, we can implement or we can realize the mix column. One more thing here is another control signal is required, which is the let's say last bit of the mix column here, last bit for multiply by 2, means that when you shift everything to the left for the multiply by 2, the LSB is always 0, right? This applies actually, this control signal plays that role. And even in total, we need 1,776 clock cycles to completely apply or perform the full of encryption function. It's pretty lot, you know. In case of the key scheduling, it's actually this is the most different architecture that we have compared to the state of the art. It has only one scan flip-flop. All other 127 other flip-flops are just normal flip-flops. And also we have one clock gating because we have to stop this when the mixed column and shift rows are operated. Compared to all other works that have been done at state of the art, that when, for instance, shift rows or mixed column are performed, then the key scheduling is applied. Here we perform the key scheduling at the same time with the with the sub bytes, with the add-on key and the sub bytes. Meaning that in 128 clock cycles, that the add-on key and sub bytes and the state is performed, we also apply here or key scheduling. The point here is that we need a sparks for the state only in one clock cycle out of 8, and then we have other 7 clock cycles per byte to use the sparks for the key scheduling. It's pretty efficient. We have only 4 XNOR and 4 NAND gates plus 2 multiplexer, and then we have also 7 extra registers here. It's also shared with that with those 4 green registers that I showed required for the mixed column. Of course, the multiplexer here are not shown, but we need also one clock gating to stop this fully during the mixed column and the shift rows operation. The same architecture when the encryption and decryption should be supported is more complicated. I'm not going to explain all the details here. The point here is that the mixed column is implemented, mixed column inverse is implemented similar to the atomic AES. Means that 3 times mixed column means mixed column inverse, and also we implemented the shift rows inverse with the same concept. Means that we apply the shift rows 3 times, and then you have shift rows inverse. For that reason, of course, we lose latency. Means that we will definitely have pretty high latency. This is the result using all those 5 process technologies that I have explained. One point that you can see here is that even with the same HDL, same design, just synthesized by different process technologies, you see extremely high different values. For instance, 1,560 compared to 1,980. It is 400 different gate equivalents just by changing the library. We try to find the reason, actually the reason we think that is coming from the size of the NAND gate, because the definition of the gate equivalence, that the size of the circuit divided by the size of the NAND gate, the smallest NAND gate. And then you can see that in the IBM 130, if you compare it with the UMC 130, you see that the size of the NAND gate is larger, means that it directly affects the gate equivalence of your circuit, then the gate equivalence of your circuit will be smaller. And just as a note, this is the same library that NSA used to benchmark the Simon and spec. Yeah, you may think that why. This actually tells us one conclusion that we should not actually implement different designs and then synthesize them by different libraries and then say my implementation is smaller or worse, just considering the gate equivalence. Of course, gate equivalence has been defined before in VLSI community to be able to check somehow given idea that whether which design is better or which design is worse. But probably in this case doesn't make sense much. Because you can see here the atomic AES version 2, the same design just synthesized by ST Microelectronics 90 nanometer of 65 nanometer, you gain 400 gate equivalents. As a note, we have used the AESS box, the design of Visconti, Schiavo, and Peralta for the just encryption means only just a SPOX forward a SPOX, which is a pretty optimized design. And for the encryption decryption, we have used the Canrod SPOX, which was the supporting both forward and inverse of the SPOX. And what is also important is that here, if you see here, there's just the single bit serial implementation of the AES encryption, also encryption, decryption. Most of the time, particularly only for encryption only, we have most of the time lower than 2,000 gate equivalents, which actually tells us whether we can consider AES now as a lightweight cipher. If we can suppose that the 2,000 gate equivalence has been defined to say whether the design or whether a cipher is lightweight or not. In case of present, the same principle has been applied on the SPOCs, and then the diffusion layer is a bit different. It's a bit permutation. This is a pretty known systematic with a systematic architecture of the permutation. And we could not actually perform this very easily, and then we came up with a two-level permutation, which you first sort. First MSBs are going here, and then second bits of every row of the state of the present cipher, and then the third MSB, and then finally the LSBs. And then after doing this sort, you do swap, means that diagonally you swap the nibbles. Here you can see the 4, 5, 6, 7 is swapped by 0, 1, 2, 3. Here, these two are swapped, or these two are swapped by these two, and so on. And then in 2 steps, you can apply also this bit permutation of the present. I can just comment that this is the same concept, which is independently found by the second talk of this session, present runs fast. This is the benchmark. Again, we can be a smaller, but of course, with the cost of the latency, we need pretty much number of clock cycles, but we can decrease the area. In case of a skinny, very shortly, the first glance is that, yeah, iterative SPOCs helps. But actually, this is not true. In reality, the parallel technique works better. The reason is that it's not fully iterative if you look at the first round and the second round and third round or third iteration of the SPOCs. This is the same, but the last one is different, means that the permutation at the end is different. This actually makes our work harder to implement a fully serially architecture. Then the SPOCs itself was small enough, then parallel implementation was efficient enough. And then at the same time, bit serial is already slow, and then it becomes 4 times slower if you want to implement this again serially. And then it was not motivating that much, and the same actually has been seen by the 8-bit variant. This is my last slide. If I want to conclude what we have done, first of all, we can say that the bit serial and also scalable architecture is not anymore a monopoly by Simon and Speck. We can implement the other ciphers. Of course, sometimes it's ad hoc, particularly for the diffusion layer. And iterative SPOCs not necessarily helps unless it's completely iterative without any exception. A small SPOCs actually are used in lightweight cryptography. For instance, we have seen yesterday the gift, which has a smaller SPOCs than the present. Then it doesn't probably make sense to serialize the SPOCs, particularly for those SPOCs, smaller SPOCs. But actually, the diffusion layer plays more important role and the efficiency of the bit serialized architecture. For instance, consider 64-bit state and 128-bit key, a variant of gift, present, and skinny. The gift authors have also implemented bit serialized architecture based on our concept. And you see that the skinny is smaller than present, present is smaller than gift. One reason is coming from, for instance, for the case of gift, coming from the permutation of the gift. If you remember, I showed a permutation of the present, which was systematic and helped us to have a 2-level permutation. But here for the gift, you don't see that structure, which makes it more difficult to implement the bit serially. Of course, we have very high latency in this bit serial architecture, but we know that it increases the energy pretty much. I mean, it's definitely not suitable for low energy application, but we expected low power consumption, particularly for RFID passive tags. If the amount of power consumption is limited, it might be helpful. Thank you for your attention.
Thank you very much. Are there questions for Amir? There's one there.
Thank you for the talk. Did you consider to use latches instead of DFF to reduce again the design?
No, we have not considered using the latches instead of the flip-flops. I mean, the reason probably is, I mean, if you want to get to the reason, probably we need to talk very long, because it's a design of digital circuits. Why not flip-flop? Why not latch? But we have not considered latches, no.
Other questions? There's one there.
Is the cost of the control logic accounted for in your synthesis?
Yeah. It's completely completed. The figures, let's say the tables we have seen is considering the logic, the control logic, and I can say that it's more complicated than normal circuits, and we have put a lot of efforts on optimizing the control logic and manually actually optimizing everything using, for instance, the normal counter, how to implement the counter to make it as small as possible.
And was it synthesized with like placement methodology or just wired load model? What kind of, that makes a big difference in
this is
gate
not
mapping.
to the layout level. This is just synthesized based on the technology with the library which is given, and
so you didn't do gate mapping, or?
Gate mapping actually is done by the synthesizer, yeah.
Right, so you map the gates, right?
Map the gate definitely, but placement not. Nothing
Right,
at the
not
layout
placement,
level.
but what about the wired loads? Did you consider? No.
Usually it's not considered in our community, sorry.
Okay.
Because usually it's like this, that the synthesizer reports that which gates or which cells of the library is used, right? And then there will be a list and the sum of the area of all these gates, and then divided by the area of the NAND gate.
So the gates are not sized at all. They're all like 1x gates.
No, the gates are selected based on the drive length, drive strength, and so on. They should be, I think they should be okay unless we need to go to the back-end design, really.
Okay, thank you.
Okay, I have two questions. First, in the slide 9 in the AES architectures, you enter the bytes, byte 0, byte 4, byte 8. So you need to permute the input bytes, otherwise there will be a compatibility issue, right?
Do you mean this one?
Yeah, so first byte 0 enters, then byte 4, then byte 8.
Here the byte 0 enters, right, and then byte 1, and then 0 will be here.
Yes, followed by 4.
Sorry again?
Followed by 4, 8, 12.
Yeah. First 0 comes, and then 4, and then 8, and then 12, and then
So
1.
this is not the natural order, right? So this will make a compatibility issue if there is another circuited decryption.
This kind of ordering has been started in 2011, I believe, in one of our works that we have done, and then everybody has followed the architecture. Just that considering the ordering, changing the ordering can happen at both sides, then we stay with the same communication.
Okay. The other thing you said that maybe the reason why different technologies have different gate equivalents because NAND gate size is different, but doesn't that mean that also the gates in your design have bigger size, so it should be the same?
The gates in our design have bigger.
I mean, you use NAND gates here, so those also will be bigger if you use the different technologies.
I don't understand your question, sorry.
So here, for example, in IBM, the NAND gate is bigger than UMC.
Yep.
It means also the gates in your design should be bigger, so that shouldn't affect the number of gate equivalents.
Yeah, but it's just a NAND gate. This is not the average over the gates. This is the point. For instance, the XOR has the same gate in both libraries, but not the NAND gates. Because whole of the combinatorial circuit is not made only by the NAND gates.
Yeah, sure.
By the gates and also complex gates.
So you mean to say like we need to look at them one by one?
I would say, I mean, if I want to define such a metric, I would get an average over particular cells, and then consider this as a size for that library.
Okay, thanks.
There's one more question over there. Could someone run with the microphone?
Hello, Amir. Thanks for the talk. I was just wondering, how do masking or other protections mix with this very small design?
If we consider AES, this will not help much. Because anyway, the dominant factor of the masking is coming from the AES box, and AES box is implemented in parallel. Then if suppose that you have a threshold implementation or any other kind of the mask implementation of the AES box, it will be placed here and the other things will be serially. Then the gain is not really much high if you apply this scheme on a threshold or let's say any other masking schemes on the AES. Unless you come up with another architecture of the AES which eases AES box, which eases the bit serialization. For instance, the slide which is here on the wall, which is a bit serial architecture of the AES box, it might be useful in the case of masking.
Okay, we're already a few minutes over time. We'll take one more short question, and then I think we should stop. And
just one short question. So for all your synthesis, for all technologies, did you use the same target frequency? Or?
Yes, the same target frequency is used, and actually we did not restrict the frequency. Frequency actually means that because we target the RFID tags, passive RFID tags, which run at very low frequency, we did not restrict the design to push the design to reach very particular clock cycle. Let's say we consider 100 kilohertz, which doesn't force the synthesizer to reach particular clock cycle.
Okay, thank you.
Okay, please join me in thanking Amir and all the speakers of the session again. And then I will hand over the microphone to the chairs. To one chair.
So will you come with me? Or okay. So I was going to ask if the steering committee or the program chairs have any other closing remarks. No? Okay, so basically we just want to thank our sponsors for making this possible, and our tireless staff who is scattered across the room. And thank you all very much for coming and making this a big success. And I would like to mention that Proofs is opening its registrations outside for about 30 minutes. And finally, we should introduce the next general chair, or at least one of the next general chairs.
Thank you very much. I think we all enjoyed CHES here in Taipei very, very much. Thank you for an amazing job that you did for organizing it. And well, Ilyana and I will do our very best to follow up on this, and we're very much looking forward to welcoming you all next year in Amsterdam. Thank you.
The meeting is formally adjourned.